Okay, watch and listen carefully here, guys. Guys, watch and listen carefully here, please. All right, so is work getting done in this question? Yeah, definitely. Okay, but there's several actual energy conversions going on here. First, someone compresses a spring. Okay, and if they compress the spring, they're doing work. But when you release the spring does work. Okay, and then that energy, the spring's work changes the energy of the toy car. All right, so the toy car uses the spring to propel it across the level floor. The spring is compressed 0.23 meters, and the cart increases in speed from 1.2 meters per second to 3.1 meters per second. The cart has a mass of 650 grams. What's the force that's needed? All right, first thing we got to recognize is that mass has to be in kilograms. That's the trick in this question. Okay, 0.650 kilograms. All right, we know the initial velocity is initial speed is 1.2 meters per second. We know the final speed is 3.1 meters per second. All right, we are looking for the force that causes that change. All right, so what kind of energy is changing here? Kinetic. All right, that's the thing we got to ask ourselves first. So work equals the change in EK. All right, so we're going to now set up our formula. Okay, do I need force and distance? Oh, sorry, I forgot the distance here. 0.23 meters. All right, so force times distance is work, and change in kinetic energy is 1/2 mvf squared minus 1/2 mvi squared. I can't cancel either one of those this time because they both have an actual value. I'm looking for force, so what do I have to do with D? Divide it over to the other side. All right, so the force then is going to equal 1/2 times 0.650 times 3.1 squared minus 1/2 times 0.650 times 1.2 squared divided by 0.23 meters. Okay, so we go 0.5 times 0.650 times 3.1 squared, okay, equals minus 0.5 times 0.65 times 1.2 squared. Divide that by 0.23. All right, so we're going to need 11.5 newtons worth of force in order to make that happen. So that's how much force would be applied to the spring in order to compress it. All right, questions there? Okay. Yeah.
Does that happen with other units or just grams?
With liters?
Yeah.
Not in this unit, because we're not going to use volume in this unit for anything, but it could come up in the next unit when we're dealing with heat capacity and water and stuff, but even there, I deal mostly with mass, but it's back to grams because it's chemistry. Yeah, I mean, it could happen, and it does happen in a lot of things in physics 20. They give you grams or they give you kilograms or whatever, right? And you have to convert. I mean, those conversions should just become kind of automatic, right? You guys are lucky in that you didn't ever have to learn the imperial system, okay? Like, I was really lucky that conversion happened just after I went into school, so I didn't have to learn it either. But you sort of learned it anyway because your parents only knew it. Right? Everything was feet and inches and pounds and whatever. Right? Even now, how many of you actually know your mass in kilograms? Yeah. Nobody measures it in kilograms, right? Like, very few of us. Yeah, and we once played a joke. We once played a joke on a tournament host one time for basketball when they wanted the heights, we sent them in meters, and everyone's like, everyone was really upset because no one knew how tall everyone was, and I was like, well, that's kind of what we were trying for. No one could scout us ahead of time. Yes. We listed one guy as Yoda. That was his height. So yeah, he was a post player. Okay. Yeah, he was really short. We were really short there. All right. So what I want you guys working on now is I want you to finish up the latter questions here. I know a few of you got to those yesterday, okay? And those get to be more like work energy theorem type questions. And then below that is some more stuff on work and energy, but it's labeled, okay? So, you know, this section is going to be about force and distance. This section is going to be about MGH. This section will be about 1/2 mv squared, and then there'll be some that'll be a little bit of both. We haven't done conservation of energy yet. That's next. Okay, I just want to make sure everyone's got this work energy theorem thing down. Seemed like it from the quiz, but that was the easier of the two. So we'll find out for sure on Tuesday how we're doing with that. Jake.
I have a question.
Okay, a question.
What are those purple bowls beside you?
Purple bowls. These? That's my lunch. It's pho. Vietnamese soup. Super yummy. Yeah. I'm recording all this. Okay? And gravity is a force, so we calculate that by doing this. The force of gravity equals mass times the acceleration due to gravity, right? Because according to Newton's second law, force is mass times acceleration. So for the force of gravity, it's mass times the acceleration due to gravity. Okay, so what they're telling you, if they tell you someone's weight in newtons, is they're telling you what m times g equals, which is useful if you're using this formula. Okay, they're giving you the first part of it. Okay, so if they give you weight, they're telling you what m times g equals. Right? We talked about this the other day when we said this is why force times distance can equal m times g times h. This is force times distance, the force of gravity times a vertical distance. They're saying the same thing. Okay. Here at number 9, because number 9 is giving people some trouble. So we have, what's the mass of the arrow in that one?
0.07.
Okay, and we had a force in that one? 65 newtons. And what was the distance? 0.9 meters. Okay, so we're looking for what's the speed the arrow is going to leave the bow at. So when I pull back a bow, obviously I'm doing work, okay, because I have a force and a distance here. Okay, and I'm trying to find out how much that work is going to change the kinetic energy of the arrow. Because once I release the bow will do work on the arrow and transfer all the energy I put into it to the arrow. Okay, so work is going to equal the change in kinetic energy of the arrow. That's going to mean force times distance equals 1/2 mvf squared minus 1/2 mvi squared. But what's the initial kinetic energy of the arrow? 0. It's sitting in the bow not doing anything. So I don't even need to write that. What I'm looking for is Vf. Okay, I have M and I have D and F. So all I have to do is isolate Vf. So I'm going to divide both sides by half of M. And then what? Square root. Okay, that'll leave me with Vf. So then I'm going to go 65 times 0.9. Okay, that's force times distance, divided by 1/2 times 0.075 kilograms. The key to this is you have to bracket this and bracket that. Otherwise, your calculator will do order of operations and mess it up. All right, so we're going to have 65 times 0.9, okay, divided by 0.5 times 0.075, and then I'm going to square root that answer. Right, and I get 39.5 meters per second. Yeah? 7? Yeah. Okay, so here's the trick with number 7. I put in extraneous information to see if you could pick out what was important. What is the reference point? The ground. So in question A, it says, find the work done by gravity when the shot reaches 2.13 meters. Gravity is taking the kinetic energy away from this shot put. Okay, it's turning it into gravitational potential energy, essentially. Right? So the height I want to use is 2.13 meters. Right? And then it's just m times g. Well, we just said that m times g is the weight of the shot put. So that's the 71.1 newtons. So for this question, okay, what I do is I know that my m times g is 71.1 newtons, and I know that my height is 2.13 meters. How much work is done in getting it to 2.13 meters is the change in the potential energy. So work equals m times g times hf minus 0, because on the ground, the shot put had no energy. Okay, so all I have to do is multiply those numbers. 71.1 times, okay, because I already have those together, times 2.13.
Okay, so if you multiply mass and gravity, you get the weight.
Right.
All right.
That's what your weight is, the force of gravity acting on your mass. That's what I was saying to David. Like if I have a mass of 80 kilograms, that just describes how much of me there is. The only reason that how much of me there is can do anything is because gravity pulls on it, right? So if I stand on your chest, you feel 790 newtons of force, right? You don't feel 80 kilograms of mass, because if I did that same trick on the moon, it wouldn't be as bad, right? I'd still be 80 kilograms, but the force would be a lot less.
Right.